All right, we're in section 7.3. Now, I didn't cover for your knowledge section 7.1 and 7.2, which dealt with sets and Venn diagrams. And I'm going to give you a small synopsis of the use of sets. It's finite, in other words, it's a specific number. To draw a diagram in the form of a Venn diagram to show relationships. So that's what I'm going to do first. Um, and and like I said, the set, they're usually capital letters in a generic form or names. Names, categories, etc. All right. So we have that condition there. That's what sets are, A and B. And then what we have uh, is a universal set. And that is the listing of all elements in the study. That means the ones that are in A and B and C and not in any of the sets. They're the ones that float around it. So now let's talk about the pictures and tell me what you see, right? So here's our universal set of a study, and we have set A and set B. Okay, in the two sets, we notice that there's an overlapping situation. Meaning, what this means is there are elements in set A that also exist in set B. Okay, so it's overlapping and that's shared. And you don't want to ever duplicate numbers because it'll give you wrong probability, because that's what we're going to be doing, introduction to probability. Then we have this one, and this one makes it very nice. Right. This one says I got a universal set. I have my A and B, and what do we notice? Oh, they are disjoint. No shared elements. Between set A and set B. Okay, this is called mutually exclusive. They share nothing. The first one, overlapping, is not mutually exclusive. It is overlapping. They share something. So, and this is dependent. And this is a dependent system. set A is congruent to set B in all elements. All elements in A are in elements of B. So let's look at something here, an example, and then you can see uh, all the elements in a quantity. So let's look at this one. It's pretend data. Now we're talking data, and so here we have males, engineering, and then we have the numbers 604, 39, and these are males in the study, 451, because they're not female. So 451 are the males that are not engineers, because that's what the 410 is, right? So from this, we can figure out that the total females, set of females, is 604 plus the 39, 643 females. And then as um, engineers, okay, so as engineers, female, well, then we would know that would be 39 out of that 643. And what we have here is the distinction of percentage, a percentage of how many females in this particular study, and maybe it was at a university, and they could say, okay, well, now we know there's 39 out of 643 females in the engineering courses. And that's a probability of a specific subgrouping in the study. So now we're getting the introduction to probability. All right. So we're going to talk first of sample space. This is that universal set. Is all elements. A specific study uh, to analyze with theoretical or experimental um, studies, experimental studies. And we're going to get probability out of this whole thing. Experiment, the trials done on on you can be on, would I put that? It's the trials on the interest study. I'm going to give you some examples here. Supposing we have a drug. So we have some take the drug, and some do not have, some take a placebo, it's a sugar pill. All right. So, or uh, we can roll a dice, roll a die multiple times to prove uh, the chance of rolling 5. So we know that the die has 1, 2, 3, 4, 5, and 6. And each one is likely to happen. This is this universal set. And we want the 5. Well, there's only one 5 out of 6 sides. So we want to make sure we do enough tests to say that, yes, it's true. We have a 1 in 5 chance to get a 5 rolling a die. Okay, those are trials. So these are done to prove or disprove or not prove that something is happening to whatever. Climate change is the big one, and so that has been on our radar for quite a while. Okay, outcomes. Outcomes. These are the measured results from the trials. These are quantitative. It's counted. All right. Cardinal number. The cardinal number is the little n in front of whatever the set is. And the cardinal number is the total number of trials. And that's very important. How many did we do to test? All right. So now we're going to talk about a sample space, all the possible outcomes. All right. So in this case, uh, write a sample space for the random experiment. So the sample space is the universal space. So here we go. A student is asked how many points she earned on a recent 76-point test. Well, she can earn a 0, a 1, a 2, a 3, and we use an ellipse to prove that it goes on to 74, 75, and 76. So there are 77 possibilities of what she had gotten on that exam. All right, so everybody see that? All right, the sample space of an experiment where a coin is tossed and a four-sided die is rolled. All right, the sample space for the coin is a heads or a tail, right? Heads or tail. All right, so let's see, hold on. Okay, and a four-sided die is rolled. Okay, four-sided. That means 1 through 4. Don't has 4 sides. I don't know how you get that, but that's what they wrote. All right, so now we're going to do the sample space. Our first flipping of the coin could be a head, and then we could do a 1. Then I could have a head, and I could do a 2. I do a head, and I could get the 3. I get the head, and I could do a 4. Now the tail, and I could get a 1. A tail, and I could get the 2. A tail, and I could get the 3. A tail, and I could get the 4. All right. So in this case, we have, this is our set, our sample space. Our sample space is going to be the set of head and 1, head and 2, head and 3, head and 4, tail and 1, tail and 2, tail and 3, tail and 4. Now this is the theoretical outcomes of what could happen if we were flipping a coin and rolling a 4-sided die. Events. Events. In an event, we're talking about a desired outcome. A desired outcome. I should say it's the stated. Expectation of a specific outcome. Specific outcome. All right, I like that. That's pretty close. A specific outcome. All right. So an event is what we want to have happen. Okay. Like in this case up here, if I had all of these all of these outcomes, well, what would be the event I'd want? I'd want to toss a tails and roll a 3. What are my chances of doing that? That's the event. All right. So here are set operations for events. Let E and F be events for the sample space S. E intersects F. Uh, F and if they have this symbol though in the Venn, it's intersect, like the overlapping. But so that would be the and. So like we said above on the overlapping female engineers. This one here in Venn diagram form says union. So that means that we add. In the and, we multiply. In the union, we add the individual occurrences. Right. A prime E prime, not that event. Everything else, but not that event to occur. Okay, I'll make it simpler when we get to the examples. Mutually exclusive means that E intersects F as the empty set. That's called the empty set or null set. Oops. So there's nothing shared. All right, let's see what kind of damage we can go into on this probability. All right, so let's see what I have. All right, an unprepared student takes a 3-question true-false quiz. The student guesses the answers to all 3 questions, so each answer is equally likely to be correct or wrong. All right, so there's only 2 outputs, correct or wrong. Write out the sample space with equally likely outcomes if possible. Then give the value of whether the outcome is S of in S are equally likely. Let C represent correct and W represent wrong. So if the best scenario on the guess is that the win and the win and the win. Wrong, right? I'm sorry, wrong. Okay, well, then we could have the wrong and the wrong and the correct. Then we could have the wrong, the correct, and the correct. All right, and then what else could we have? All right, so that's assuming that occurs. Now we can have on this problem, okay, we could then have correct, 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 wrong, correct, wrong, wrong. So we have 6 in the sample space. Right. So the cardinality of the sample space, N of S, is 6. Okay, so we got that? Are the outcomes in S equally likely? Yes. Question is independent from the other, from each other. In other words, the answer of one doesn't affect the other. They're all just questions. Write the following event in set notation. The student gets all 3 answers wrong. There's only one in that set of the event. All right, now it says, write the event and set. The student gets exactly 2 wrong answers. Okay, 2 wrong. So we're coming up here. We got this one and we got this one. 2. That would be wrong, wrong, correct. Oops, I made a mistake here. Sorry about that. We have to come back up here. It's not 6, it's 8. Because we can have wrong, correct, wrong. And I forgot that one. And this one is correct, wrong, correct. And I left that off. It's 8. Sorry, sorry, sorry. So, luckily, it doesn't affect what we're doing in the sample space, except right here. Exactly 2 answers wrong. And so it's this one, this one, this one, and that one. Now we got it. 4. They are, I mean, only, oh, this one. Exactly 2 correct. Wrong. And we had 4 of them. Right. The student gets only the third answer wrong. Only the third answer wrong. So CCW, 1. All right. So now that we've got that, and I'm sorry about having forgotten that one, I apologize. The probability now is the mathematical ratio of desired event over total sample space. All right. Well, this is how it's written. The uh, cardinality of E over the cardinality of the sample space. All right. So now we got it. So here we have an enclosed, in case you're not familiar, and this is a deck of cards. This is a deck of cards. And I'm going to stop right there because I've been on here. I'll start right here on part B. And thank you very much for listening. You'll have to go to the other one. It's a heavy section, a lot of explanation, and we've done a good job. Thank you for listening.